This is the ROS Developers Podcast, episode 100. Wait a minute. 100 already? Okay. I didn't know that. That caught me by surprise. So we'll have to think about something for the 100. Okay, we'll see. Let's go.
The ROS Developers Podcast. The ROS Developers. The ROS Developers Podcast. The ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this episode to all those people that think that robots, which are remotely controlled by a human, are not really robots, but just machines. So if you are one that dreams with robots that autonomously move around in our human spaces and accomplish their tasks successfully without human intervention, then this episode is dedicated to you. And in this episode, we are going to learn about how ROS can help in achieving the dream goal of building autonomous robots. But before that, let me tell you that in case that you want to, okay, so I've got some problems here. Yes, yeah. So in case that you want to be one of the creators of autonomous robots of the future, but lack the skills for that, let me recommend you our 6 months robotics developer job ready program. It's a program that teaches you in 6 months all the skills that you need in order to work creating intelligent autonomous robots. We start from zero, teaching you about Python, C++, and the maths that you are going to need. And then we move to ROS-based navigation, perception, simulation, and manipulation. Then we teach you the theory of robotics and move to the learning of the developer tools for robotics that you are going to need, like, for example, Docker, Git, continuous integration, and some others. We conclude the program with an internship in a robotics company worldwide. Then it is an intensive program that you can do full-time in 6 months or part-time in 1 year. Check the link below, and I will give you the link on the notes of the show. And it is an opportunity, just right now, to get up to speed in a short amount of time. Okay, so now, what do we have to do with this? Let me introduce you, Patrick Musau, who is a graduated research assistant at the Institute of Software Integrated Systems of Vanderbilt University at the USA. He recently delivered an interesting presentation at the ROS World 2021 entitled Towards Assured Autonomy with ROS. Let's learn how ROS and Gazebo can help us to build the autonomous robots of the future. Welcome to the podcast, Patrick.
Yeah, thanks so much for having me.
Oh, my pleasure. So the first thing that I learned from you was that you were one of the candidates for the TSC, but then afterwards, then I was checking, okay, so who is this guy? And then I saw your presentation, your video. It was released by Open Robotics on Vimeo about your presentation at the ROS World. And I thought that, wow, that subject is very, very interesting, but also very, that has not been dealt with just in a few places. So, and it's an open question for developing autonomous robots. And then, based on that, I would like to ask you, what is that you mean by assured autonomy?
Yeah, I think that's a great question. So over the last couple of years, we've really seen that autonomous systems have taken off in many industries like autonomous driving, drones, and other places. And there's been a lot of really cool technology development. But one of the things that we haven't really seen is a large set of safety assurance approaches for these systems. So a lot of these systems work in like uncertain and dynamic environments, and it's really hard to reason about their correctness. So the Assured Autonomy program is really a program that is dedicated towards developing these kinds of techniques. So how do you go about demonstrating that an autonomous system is correct? How do you do that from a component-based analysis as well as a system-based analysis?
Okay, so it's not to learn how to do autonomous robots more autonomous, but it's about how to ensure to the buyers or to the people that is going to buy that this is really autonomous and it's not going to do crazy things.
Yeah, definitely. I think like there's a lot of promise for these technologies, especially within like the exploration space. But how do you deploy these systems in like safety critical settings? So how do you go about demonstrating that if you have a self-driving car, that it will actually navigate in the environment that you designed it for? So those are the kinds of questions that we're really trying to answer through this program.
Okay. And then according to your opinion as an expert, then what's the biggest problem in the creation of an autonomous system for everyday life?
Yeah, I think it'll be biased since I've come from the perspective of a safety engineer or someone studying the safety assurance of these approaches. But I think that is honestly one of the hardest challenges that we have to face. I think there's also like a bunch of different hard machine learning and AI problems that we're still trying to figure out. So how do you design models that generalize to multiple scenarios? How do you make sure that they're correct? But yeah, safety for me right now is probably one of the most critical issues that we're still working towards achieving. Okay. I know NHTSA and all these other government agencies have really dedicated a lot of work towards answering this question. And you can even see in the literature that there's just been an explosion of so much work within safety. But I think it's a critical problem.
Yes. Okay, yeah. So that question was a little bit tricky, I understand, because there are many problems that we have to solve yet for having autonomous systems. And then, of course, I wanted to see your opinion on from the point of view of safety, because you are the expert in that. So I do agree completely with you that safety is one of the problems. But could it be that we are asking too much safety to the autonomous robot, something that we are not asking to ourselves, like the bus driver, for example, that drives our kids to the school, or, I don't know, the person that is going on the street with driving normally, so maybe it's not that safe, that person. What do you think about that?
Yeah, I think that's a very interesting question. I think one of the main motivations of developing autonomous software was that we wanted to eliminate deaths within the autonomous driving space. So the whole thesis of autonomous vehicles is that they have to be better than human beings in order for us to use them. But it's also just from a system design standpoint for engineers, like let's say even that these autonomous driving vehicles did decrease the amount of people who lose their lives to accidents every year. Instead of let's say it went from 80,000 to 20,000 people. Instead of 60,000 thank you notes, we'd actually get 20,000 lawsuits. So from a different perspective, the standard for these systems is higher because we want them to be higher. Okay. The goal is to be better than the current status quo. So that's the reason the standard is so high.
Okay. Yeah, I also agree with that, with having that standard. Yes, it's unfair to robots, but what can we say? So it's your job. Robots is your job. So. Okay, and then I was watching your presentation on the ROS World, and then you were mentioning about so how you can assure that this autonomous system is not going to do crazy things, and you mentioned that the systems based on machine learning are a little bit fragile. So what do you mean by that?
I think what I meant by fragility there is that machine learning systems really can fail in unexpected ways. So over the last couple of years, we've seen even with the exploration of adversarial examples. So an adversarial example here is just making a small input that is provided, small change in the input that's provided to a machine learning model can cause it to produce an incorrect classification or just even some unexpected output. So when you have these systems within autonomous systems, they're quite fragile in that small changes in their inputs that they're receiving at runtime could cause them to do crazy things. Mm-hmm. So it's one of the things that we've even seen on Twitter or on social media where we have all of these people posting about even Tesla's new vision-based models, and just unexpected scenarios. So like, for example, a truck driving with a set of traffic lights. That's one thing that the developer might have not had thought about before that. Or the other thing was very interesting was the moon. And a vision-based component actually detecting that as a stoplight.
Yes.
So it's one of these things where like machine learning models are very powerful. They're very good when they're utilized on data that they've seen before in a training set. When you change that distribution a little bit, they start to act really funny. And that's why I say that these systems are quite fragile.
Yes, I remember that example that you mentioned about the stop sign, and some guys that they put some small stickers on the stop sign, and then the car wasn't able to detect that this was a stop sign, and then it's like, wow. But then could those systems be actually useful in the real life? Because real life is not that much based on just a set of examples, and so we have different conditions all the time. So so I know that your work is about how to comply those systems, so you can train them better, so they are not that fragile, and also you can certificate that they are going to work properly. But this is one line that we can go, or maybe there are other lines that we can go, and maybe will be more robust to those situations. What do you think about?
Yeah, I think like a lot of sometimes when we talk about adversarial examples, we're also not being too fair to the companies developing these systems. I know that a lot of these systems don't take the prediction from the machine learning model and straight input that into the vehicle. There's multiple layers of redundancy with there as well. So, for example, if your machine learning system doesn't produce that the stop sign exists there, you can compare that information against the map that these companies are also developing at runtime. Mm-hmm. So even though your machine learning model fails to predict the stop sign, your map tells you that there's a stop sign in that specific region within the map. Yeah, I think like redundancy is definitely one thing that people creating these fault tolerant systems have thought about a lot. It's not really realistic to use one point of information. You really have to use a bunch of diverse set of sensors and information to make your predictions online.
Yeah.
But even beyond that, I think a lot of there've been some really cool developments within the autonomous vehicle space of even collecting more data as the vehicle drives. So as it makes its prediction, a lot of people have designed systems that now create new data based on the actual observation that was made at that time, the prediction that was made by the machine learning model. So their models are getting better and better and better as they develop. So it's a really exciting space within the safety space, but even within the machine learning space is how these technologies are being developed. There's so much work being done.
Oh, awesome. Yes. I like the word that you mentioned. It's about the redundant systems. And yeah, I completely agree. And I think that it's also what we do as humans, but we are not conscious about that, but maybe we are also relying on a lot of information and that's why we say, oh, this is wrong. So what I'm seeing here, something is wrong. And why is wrong? Okay, so this stop sign is a fake sign. It's not real because it doesn't make any sense to have this here, or because I know I have passed here many times, there was no reason to put a stop sign or things, I don't know, some other ideas in our brain.
Yeah, definitely. Redundancy is huge.
Redundancy, yeah. So it's also fair that the systems, they use it, of course. Okay, and then you in order to promote those assured systems, you are working in a project which is promoted by DARPA, which is called the DARPA Assured Autonomy Project. What can you tell us about this project?
So yeah, this project really started, I think, in 2016. It's being worked on by many universities across the states. It's a huge problem. It's a huge program by DARPA as well. So Vanderbilt is part of it. There's a lot of other universities, so Berkeley, University of Pennsylvania. I know Stanford's doing it on the West Coast. And there are many different tracks within this program as well. So I think the assured autonomy problem is very huge. So you can think about it from like a system testing standpoint. You can think about, okay, if we have all of these different methods for like reasoning about our systems, How do we synthesize these bodies of evidence to the stakeholders so that they can actually analyze it? What are the kinds of evidence that we need to analyze in order to show that an autonomous system is actually correct? So there's a bunch of different methods being developed. For example, like I can give you a work out of Stanford where they're actually out of Berkeley, where they're coming up with methods for scene generation. So if you have an autonomous system that you are trying to analyze for, like, let's say working in an urban setting, right?
Yeah.
How do you explore different changes to that scene and analyze your system? So for example, how do you change weather conditions? How do you change how many pedestrians are in the scenario? What about different lighting conditions? What about all these different models of just like how do vehicles operate within that setting? So they're designing these languages to come up with scene description languages so that you can do these types of analyses. I know Stanford's doing some work around stress testing. So how do you find the areas of your system design that are wrong? So, and how do you rigorously test that? On our end, we're trying to come up with a set of tool chains where you can do model-based development at Vanderbilt. So how do you start with the requirements outlined for your system? How do you design models of your system and then analyze those models across those requirements for those? And then how do you develop a tool chain for the developers of these autonomous systems to be able to do these types of analyses? So there's different focus groups within the DARPA Assured Autonomy program. And it's pretty big, and it's been going on for a couple of years. And yeah.
Okay, and then this tool chain that you mentioned is one of the parts that you presented at the ROS World. And so it's not clear to me if that tool chain it contains software. When you mean tool chain, you mean software tools or also tools? Because you mentioned a lot of things that we need to take into account into the scene. So it's like also tools for deciding how we are going to create our environment so we can certify that our product finally is going to work in this environment, but also in the real life with small differences. Yes.
So one of the things that the tool chain allows you to do is develop the models of your system. So for example, like say you have a vehicle. What is the modeling paradigm you're doing for modeling that system? So are you using a kinematic bicycle model? Are you using all these different things to model how the vehicle operates, right? The other thing is, like, let's say you have
Wait a second. Mm-hmm. You mean how this model operates in physical terms?
Yes.
Okay. But that's the role of the simulator, isn't it?
So yeah, there's two parts. So there's a simulator that can do that as well, but you also need to be able to use those models to do these types of analyses for correctness. Mm-hmm. So not only does the simulator have this model, right, mm-hmm. which might be more complex than the model that you're using in your analysis, because typically that's the way it works.
Okay.
But in order to make predictions about how your system operates, you need a model of your system.
Oh,
right?
Okay.
So you have a model of the physical dynamics, but you also need to have a model of how the software interacts.
Yeah, that's right.
So this is where we go within our field called hybrid systems. So autonomous systems have this coupled nature between physical dynamics and software, right? Mm-hmm. And how do those two pieces interact? Because if you're really going to reason about the correctness of a system, you need to understand how they interact.
Yes.
So the tools that do these types of analysis require a model of the physical dynamics, and they also require some model of the software as well.
Okay.
So these are the types of things that the toolchain allows you to do. So what's your physical
models
of your physical system? What are your models of your system? And if we do an analysis based on, like, let's say we're doing it for like a collision avoidance task, right? Mm-hmm. Does the component that I designed for this vehicle actually lead it to avoid collisions? So that's a type of analysis you can do.
Okay.
The other thing is, like, let's say you want to train machine learning models, right?
Okay.
So let's say you can also use your simulator, right, to run your system, collect data, right, save that data, and then the toolchain allows you to train machine learning models within it. So based on that data, right? And the reason we allow you to do those things is because as part of the toolchain, we're also developing methods for developing assurance monitors for those machine learning models. Uh-huh. So we can develop models that tell you whether or not the inputs provided to your network at runtime correspond to the training data. So that's an assurance monitor.
Okay.
So if you use our system to train a machine learning model, we also train these models for you alongside. So there's a bunch of different things that this toolchain allows you to do. That I'm really basically only scratching the surface.
Yeah, I understand. It's a podcast. So the guys that are listening to us now, probably they are on the car or on the gym. So we cannot explode their minds right now. So this is for them to visit then afterwards your webpage and all the information that we are going to put on the show notes related to you and your project, and then go afterwards. But then those tools, they are open source. So can we get them installed in our computer or use them in our projects?
Yeah, a lot of these things we publish them publicly. A lot of the tools are also open source. We're actually working on developing a website later this month that we're going to release online. So anyone who wants to learn about these methods, the Toolchain can use it as well. The goal of this project is to give back to people who want to do these kinds of works and move this research forward. I know it's only been 6 years now that the project's been going on, but I know there's a lot of work that still have to be done. So, a lot of this stuff is open source.
Okay, that's awesome, and I definitely have to look at it and then see, because I think that robots, they are going to be everywhere in our close future, and then the way to go is to assure that they are secure and that they are going to do whatever they need to do, they have to do. So that's one of the lines, and also I'm very interested about that in terms of teaching our students about this, because the companies, they are going to require that they know about this. This way, for example, okay, before going into that, another question is, before I forget, so what's the role of ROS in all this? Because we have been talking here a lot already, but ROS doesn't appear anywhere. Is ROS useful in any way? Is included into this toolchain?
So the whole toolchain is based on ROS. ROS has ROS has been huge for us. I think if we had to go and develop all of the navigation packages ourselves, or some of the localization packages, or even just the amount of things like the transforms that ROS provides as well, it would have been a huge overtake. But there's a wealth of information that the ROS community has developed that we leverage.
Exactly.
So the platforms we are considering right now are this 1/10 scale autonomous car called the F-110 that is completely ROS based. We have some unmanned underwater vehicles developed by Blue Robotics that's also ROS based.
Including the simulation also?
Yes. So the Blue ROV simulation, I believe, is open source. And if that was not open, we also use UUV Sim, which I know is pretty popular in the community as well.
Which one? Sorry?
UUV Sim.
UUV Sim. Okay.
Yes.
In the community, you mean in the community of underwater robotics?
Yes, in underwater.
Yeah, exactly. Yeah.
Definitely. So a lot of, right now, it's all ROS 1 based, but hopefully we'll start moving it to ROS 2, because ROS 2 is just exciting as a project. It's incredible.
Yes. I think that this year, 2022, is the year of ROS 2.
Yes, it is.
2022, so so it couldn't be more twos. Well, yes, another one, but this is for 200 years from now, so we'll see. No, but actually, I made a report, and it's in a video on YouTube where I analyzed what happened with ROS along the year, and then my conclusion was that everybody was starting to transition into ROS 2 in 2021. So I expect 2022 to be the ROS 2 year, really.
Yeah, definitely.
Okay, so sorry.
Go ahead.
You should change your framework, your tool chain into ROS 2 then.
Yes, definitely. It's going to require a lot of work, but at the same time, I think it'll be worth it.
Yes, and a lot of fun, I think. A lot of fun.
Yeah, definitely.
Okay, very good. Then let me see, because we have been jumping along the questions, and then I get lost. You kind of mentioned this, but you were mentioning the answer to this question, and still I don't have it clear. So how can you really provide assured autonomy?
So I think...
Because always it's going to be trained in your... Even if you have this scene language where you express. So you cannot take into account all the possible situations, and so well, okay. So I don't know how it can be provided or ensure or provided maybe a measurement of the amount of we can assure that this is 98% secure or 99%.
Mm-hmm. Yeah, I think this is an interesting question. I think from like even just over the years, from a philosophical standpoint, I don't think like perfect safety is a realizable goal, because the one thing is, as we see with autonomous systems, is to do these types of analyses. One, you have to analyze a very high dimensional space. Yeah. The set of behaviors that an autonomous vehicle can take, even within like a single city, is infinite. Yeah. So the one thing is, the idea is to develop safety arguments in proportion to the resources or the risks. Mm-hmm. So you can say, the way this is typically done, and within the model safety engineering literature, is you develop assurance cases. So let's say you have a requirement that your vehicle, for example, avoids all collisions with obstacles within its environment. Mm-hmm. What you really need to develop is an assurance case. So what are the types of evidence that show that your system actually do that? So like, let's say, okay, you ran your system tests, or your formal verification of the models of the system say that it works. Okay. Or you have redundant like components that make sure that this is happening. But basically what you do is you do all these types of analysis. So you can do verification, you can do simulation, you can do integration testing, you can do system testing, and you amass this evidence, right? Okay. And that evidence is the assurance that that particular requirement has been satisfied. Okay. But that's only one requirement. So you list, when you're looking at the document with all your requirements, you synthesize all these levels of evidence for that. And then there's a lot of methods within model-based engineering that allow you to develop like these risk scores for the whole system, or for assuring the trustworthiness. There's like a lot of literature that's been done for traditional systems. Yes,
for like planes or spatial missions or something like that. Yeah,
something like that. So there's a really like rich history of doing that for traditional systems. Mm-hmm. The things that the Assured Autonomy project was doing is, okay, there didn't really exist too many testing spaces for machine learning models. Mm-hmm. There really didn't exist too many models for formal verification of machine learning models. So we were developing these types of techniques so that they could be leveraged within frameworks like that.
Oh, okay.
So it's not too much different between that. But we're just developing the technologies that allow you to do these types of analyses, and then you put them within that framework.
Okay. Now makes perfect sense. Yes. Because machine learning systems is a new module that exists now that we can plug into any other system, right? And yes. Then let's say like a plane, for example, and then for assuring security in a plane, there are those procedures that already exist. But when you plug this, then something changes, nobody knows how to do it, and then you come and then you say, oh, guys, you have to do it like this. For machine learning systems, to certify them in your whole plane, then you have to do it like this. Right?
Yes.
Okay, I got it.
So it plugs into the old framework.
Into the whole framework, exactly. I got it. Okay, great. Yes, and actually we cannot ask the same thing to individuals, because individuals, we can be depressed or have problems or so on, and also do some strange things in given strange circumstances. Then let me check here. Yes, so we have covered that question also. Okay, so you mentioned in your presentation also about the challenges in developing such kind of assured systems. Can you give us a short list of those challenges?
Yeah, I think so. The one is just like autonomous systems have this inherent interaction between the physical world and then software, right? So we have some really good approaches for verifying that software is correct. There's a lot of like history of software engineering processes. How do you test? How do you do all these things? On the simulation side, we also have a rich set of like numerical approaches for like simulating physical dynamics. Mm-hmm. How do you do analysis of those things? But the challenge is, how do you really let those two really effective methods meet? Because a lot of the challenges happen at the interface of those two things. So how do you model a system that interacts both in software and also interacts in the physical world? And those analyses are very difficult. So that's one challenge point.
Okay.
The other challenge point for these systems is like typically when you're driving a car, right? Once you design the software and you deploy it on the vehicle, it doesn't really change. You make updates occasionally, right, to like the system software, but it doesn't really change, right?
Yeah.
With an autonomous system now, like let's say you have a system that's learning online. That is no longer the case. You deploy the software on the vehicle, but that software may evolve. So that's one challenge. So like a lot of approaches that we've developed in the past is like, okay, we work very hard to make sure that our software is correct before we deploy it.
Yes,
right?
That's right. Yeah.
But for a machine learning, like let's say we have an autonomous system that is learning online, for example, you deploy your software and then your software changes online. So this is a whole new framework. So it's a whole new paradigm. The other thing is like, let's say you have traditional software. When you make small changes to the system, they're small in a sense that if you change one thing in like your new software, you don't have to go and rerun your entire analysis on the whole system if it's just software.
Okay.
Right? But if you retrain a machine learning model, because they're learning from these high dimensional nonlinear spaces, changing one thing changes everything about your model, potentially.
Yeah.
So you can't really say that these small incremental changes, you basically have to rerun your analysis.
Yes, exactly.
Which is a very expensive approach. So that's another challenge with we're going as part of that space. And then the final thing is even coming up with requirements to analyze for machine learning models is very difficult. Like, how would you write down the specification that a computer vision classifier for classifier is correct? What does that look like, right? How do you define that, like, in code? How do I analyze that a classifier is correct? Just writing down that requirement is as hard as doing the analysis.
Yes.
So it's a very challenging thing. So
okay,
there's a lot of different challenges, but it's a really exciting space.
Yes, and I can feel that you like it. That you are in your. We say in Spanish, we say that estás en tu salsa. So that you feel like a fish in the water. You know, it looks like you like it a lot.
I like that saying.
Very good, very good. And then actually, when I saw your presentation on the listing of the ROS World, I say, okay, I don't understand why this presentation is here in the ROS World and so on, because I didn't know about the subject of Assured, but I thought, autonomous system to make autonomous systems. And then, I mean, yeah, we have discussed about that, a lot of things, but then now going deep into, now that makes a lot of sense, Actually, there is one company, it's called Apex AI, that they are kind of doing this, but for the operating system of the autonomous cars. So they want to certify that this is safe. This is not that complex as what you mentioned, because, I mean, it's a lot, very, very complex to do it. It's very complex, but it's on the software layer that doesn't evolve, as you mentioned, and it's a traditional software. So it's going into that direction, what I mean.
Oh, that's a really exciting work. I'm excited to see what they do.
Yeah, so it's open. They have taken the ROS 2, and then they created their own modifications and created the certifications for being used in autonomous cars and other vehicles or other systems also.
Oh, that's really exciting work. I'll have to go look it up.
They are hiring now.
Oh, no way!
Yes. So maybe it's an opportunity for you.
Yeah.
I don't know. Yeah. Just saying.
I appreciate that.
Okay, so you mentioned about the adversarial examples also, and you have mentioned before in the podcast, I mean, about we have already explained. You have already explained, and then we have another question, which is about reachability analysis. What is that?
Yeah, so reachability analysis is this model checking approach. So the idea there is, how do you explore the set of states that a system could achieve over a finite time horizon? In
the world, let's say.
So it's really confined to specific situations. So I'll get into that.
Okay.
So basically, like, you have a model of your system, right? And typically, like, let's say you want to simulate for example, a vehicle going forward, right? You have some control input you provide to it, and then you can predict where the vehicle will be, right?
Okay.
But that's for a single point, right? For a single initial condition. So
Yes.
you control input where the vehicle is and where it will be in the future.
Yes.
So reachability analysis is we take that point and we expand it. So instead of just being a single point, let's reason about sets, right?
Okay.
So if we have, instead of just a single point, what if my vehicle is within a particular box? What is the set of states that my vehicle could achieve in the future from that box? So the output of that is the set of reachable states.
Okay.
And you have assumptions about what your control input is. So like, let's say we're just taking left turns. So any point within that box, where will I be if I only take a left turn?
Okay.
So that's the set of reachable states. But why this is important is these analyses are really used to analyze safety specifications, right? So like, let's say you have a component that does a collision avoidance for like, you want it to avoid obstacles and you know the location of the obstacle. And you have a component that does that collision avoidance, that provides those control inputs to your vehicle so that it avoids it. One of the questions you could answer through reachability analysis is, does my vehicle really succeed in avoiding this obstacle for all the points within this box, for example, for one region within the state space? And when you compute all the set of the reachable states, you can look and see if any of those states intersect with the obstacle.
Okay.
If not, then now you have a proof that your component works. And if not, then you have to go back and see, okay, which of these trajectories led to a collision, and you can go back and refine your system. So that's typically how you use reachability analysis. But it's really just a version of predicting all the sets that a system can attain based on some assumptions of how it operates and where it will be in the future.
Yeah, the actions that can perform and under the conditions that it can have in a set that you have specified. Okay. Now I understand. Okay, and another thing. Okay, and is this related with the non-conformity score? So the non-conformity score would be the number of trajectories that collide or something like that?
So the non-conformity score is actually a different line of work.
Okay.
So, so the reachability analysis is really for like these collision avoidance type of questions, or you can do it even for neural networks. Like if I provide an image, right, and I change its pixels by this much, what are the predictions it will give me on the output? So you can analyze sets of images to do that. This non-conformity score we've actually developed for assurance monitoring. So what I mean by non-conformity is how much does this image correspond to my training data's distribution, right?
Okay.
Does it conform to that distribution is what the non-conformity score really measures. So typically when you train a machine learning model, you have your training data, you have your test data, and they come from a certain distribution, right?
Yeah.
You train them, and then your machine learning model is going to perform really well on those examples.
Yes.
But if you have let's say you train it only on dogs. Let's say you bring a cat into the distribution, your machine learning model is not going to work.
Exactly.
So the question we're trying to answer here is, how would we tell our model that this image doesn't correspond to our training distribution, so that we have a warning if it produces an errant behavior, that this model didn't come from our training distribution.
Okay.
So the way we did this was actually with a method from GANs, where you use autoencoders to basically project them into a latent space and then reconstruct them, right? So there's this formalism where you have an input, you can project it into a latent space, and then you can use that latent space to reproduce the image.
Yeah, an autoencoder, yeah.
Yes, an autoencoder, exactly. So if you form images within the training distribution, the reconstruction is pretty good.
Okay.
So the reconstruction error is very small. But let's say you had a cat image and it was trained on dogs, and you tried to reconstruct a cat image, right? It would probably look very much like a dog. So now you can already say that there's a non-conformity score.
Wow.
So that's one form of doing that. But yeah, that's the idea that we're reasoning about with this non-conformity measure.
Awesome. And then if you apply this to the stop signal that has this sticker, this non-conformity score, will be very low, right?
So the non-conformity score will be pretty high. So if it's low, if it's low, that means that it conforms to the training distribution.
Yeah, but
if it's high, then the reconstruction error is high.
Okay, but in this case, the image. Okay, I got it. Yeah, I got it. That because the score is high, then that's the reason why it gets confused by the system.
Exactly.
Yeah. Okay. Yeah. It should be low because it's not that different, but that's how it should be. But in reality, it gets confused, and then you can detect, hey, with this image, the system is going to get confused, so you can know beforehand.
Yeah, so it's a very interesting approach, and there's many different ways. This is just one of the ways that we're approaching it. But yeah, that's the idea. So if you have an image, your system should have some way of warning itself that I might not make the prediction correctly based on this image.
Okay.
So then you can start to make some mitigating actions.
Exactly. Like, hey, wait a second. Let's stop and let's connect to somebody else, or take a look around, or do whatever. Yeah. Okay. Great. Oh, so great that I understood then this, and then you explained to us also about the toolchain development and also what ROS has to do with it. So I think that we got a full picture of your presentation. Then for more information, then I'm going to put a link to your presentation also and to your contact details and so on in the show notes for people that want to learn more. Now I would like to ask you about the TSC, because you got elected recently for the ROS2 Technical Steering Committee on the, let's say, on the category of community, or the section, I don't know what's the specific...
Community representative.
Community representative, okay. And then why are you interested on that?
Yeah, I think for me, ROS has been huge. In terms of when I first started grad school, I had no idea that I wanted to do robotics. I joined one robotics competition on a whim that was being developed by the University of Pennsylvania. And I really benefited from all the documentation, all the developers in the community. I know I used the construct tutorials. I knew so many different things. And I really learned a lot of stuff from the community. I think like there's a lot of users within academia that use ROS to do their research. It's huge. And I knew that I had really seen the power of community in developing robotics applications. So one of the things was I wanted to give back. I wanted to help develop the new ROS2 and help bring the viewpoint of students in academia who are doing this research to the TSC. I know the TSC is developing a lot of cool things. They've got a different directions, and I just wanted to offer that insight that I had gained over the couple of years to help make ROS2 better for everybody. And yeah, that's mostly why I did it. I've really appreciated ROS. It's been huge in my dissertation, and now I just want to give back.
Great, awesome. Then congratulations for being
Thank you so much.
Congratulations. And so yeah, I think that we pretty much cover everything. One last question is, so if people want to hire you or discuss his projects with you, or any ideas, or would like to know more about your research and your work, how can they contact you?
Yeah, definitely. My LinkedIn is open, so please message me there. They can email me as well. And then I think I'll provide a link to my website as well. They can feel free to drop me a line. I'm more than happy to get more folks interested in this work. I think it's important, and I know there's a lot of smart people there that can really help us. So please feel free.
Okay, perfect. Thank you very much. Then, Patrick, I hope that we have the chance to meet in person on the next ROSCon.
Definitely.
I hope that this year is going to be in person. We don't know yet, but let's go for that. And thank you very much for being on the podcast.
Yeah, thank you so much for having me. I really enjoyed it. Thank you so much.
And okay, so that's all for today. So remember that if you want to support the podcast, please go to your platform, wherever you are listening to this, Spotify, Apple Podcasts, Stitcher, whatever, Google, whatever. and give us 5 stars. Also, you can contact us on an email that I will put below on the show notes and tell us what you think about the podcast, any suggestions that you have. We'd like to know more about you, your feedback, so we can improve in some sense. And that is all for today. See you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.